right, so 3.1 we talked about functions themselves, and if you remember, a function is just a relation where every input has exactly one output. So now we're going to move on to linear functions. If you notice, the linear has a word line that gives us a clue of what we're going to be talking about. So we will be talking about lines, whether a function is a line or not. So I have a few vocab words here. First one is linear equation in two variables, and this is just an equation written in the form y equals mx plus b, where m and b are constants. Okay, you've probably seen this y equals mx plus b before. This is what we call slope, why am I forgetting this? Slope-intercept form. There we go. It's called slope-intercept form, where m is my slope and b is my y-intercept. The word constant, if I say that m and b are constants, what I'm talking about is that it's just a number. So in equations we have constants and we have variables. Our variables are what change, they vary, right? Our constants stay the same, they're just numbers. So it's an equation written in the form y equals mx plus b, where m and b are numbers. So we've seen this before, right? This would just be like y equals x plus 1, or y equals 2x minus 7. Okay? It's just a linear equation that is written in this form. That's all that is. A linear function is a function where the graph is a non-vertical line. Whoops. Okay, try this again. Where the graph is a non-vertical line. The reason why I have to add in that it is a non-vertical line, if you remember yet on our 3.1 note sheet, we talked about the vertical line test, and we used the vertical line test on a vertical line, and we discovered that a vertical line is not a function, right? Because it passes the vertical line test, it failed. It passed through all of the points on our graph. And so this definition is a linear function, and so since a vertical line is not a function, it's not included as a linear function. And then another thing to note about a linear function is that it has a constant rate of change. Constant rate of change. We call this our slope, right? So in our example up here, my 2 in this form, 2 is my slope, right? This is my rate of change. My graph, my line, changes 2 spaces every time. So it goes up 2 over 1. It has a constant rate of change every single time. So if this is a linear function, a non-linear function is pretty self-explanatory. It's a function where the graph is not a line. And not a line. Where a linear function has a constant rate of change, a non-linear function does not have a constant rate of change. Not constant. So a linear function is going to increase or decrease by the same amount every single time. A non-linear function does not increase or decrease by the same amount every single time. Okay, a solution of a linear equation in two variables is an ordered pair that makes the equation true. And if you remember, ordered pairs are in parentheses. Our x value is here, our y value is next. Right, that ordered pair is together is a solution to my equation. So when I plug in x, I get out y. That is my solution. Okay, last two definitions here are both about domain. If you remember, domain is the set of all of my input values, all of my x's. And then I also had two types of graphs in 3.1. I had a discontinuous graph and a continuous graph. So my discontinuous graph was the one where they were just points were just plotted, right? So a discontinuous graph has a discrete domain. So a discrete domain is a set of inputs that consists of only certain numbers. In an interval. And I'll show you what I mean. So, my domain is all of my x values. This is when I just have a limited amount of x values. So, for example, I could have a discrete domain of 1 through 5. So 1, 2, 3, 4, and 5. This could be my domain of my function. The only, my domain for this function is a discrete domain, and it just consists of 1, 2, 3, 4, and 5. Nothing else. Just in this example, right? Those are the only numbers that I can plug in for x. On the flip side then, I could also have a continuous domain. A continuous domain goes with a continuous graph, right? And a continuous domain is a set of inputs that consists of all of the numbers in an interval. So, using my same boundaries of from 1 to 5, a continuous domain would look like this. 1 is less than or equal to x is less than or equal to 5. What this tells me is that my domain, my input values, can be anywhere from 1 to 5 and any number in between those two. So if I looked at my example from discrete domain, could I put in 3.5? Does it fit in here? No, it doesn't, right? Because my only values are 1, 2, 3, 4, and 5. 3.5 is not one of those values. It's not part of my domain. Could 3.5 fit down here? Yes, it can. I can have that be 3.5 because a continuous domain is all of those values between 1 and 5. So literally any number that falls between 1 and 5 can be an input value for my function. So, no. No. Yes, right? It works in here, it does not work in my discrete domain. Okay, this stuff is fun because it's super simple. So I'm just going to look at these graphs and decide if they're linear or nonlinear. So I look at this one first. All I see is a straight line. This is linear. My second one, I got a curve up here, right? This is nonlinear because it's not straight. It's not a straight line. Easy, straightforward, simple. I can just look at it and tell right away if it's linear or nonlinear. Okay, these require a little bit more thinking. So does the table represent a linear or nonlinear function? Well, if you remember, a linear function has a constant rate of change, right? It's going to change the same amount every single time. So what I need to do is I need to look at my outputs, my range, my y values, and see, are they changing the same way every single time? Well, if I look at my first graph, or my first table here, I go from 2 to 9, 4 to 18. Well, to get from 9 to 18, I go up 9, right? That's constant. To go from 18 to 27, oh, that's also 9, right? These happen at a constant rate of change. This is a linear function. All of my y values are 9 spaces apart. It is consistent, and it's constant. My second graph, I go from 1 to 27, and then 27 to 125. Is that a constant rate of change? No, it's not. This is a nonlinear function. Nonlinear. Okay, so it's obviously a little bit more simple to just look at a graph to decide whether or not a function is linear or not linear. So what we're going to do is we're going to take a look at these functions using Desmos to figure out if the functions are linear or nonlinear. So you can pull this up on your own if you want to, or you can just follow along with what I'm doing, but just make sure to fill in these boxes down here with if it's linear or nonlinear. So let's go to Desmos. Oh, I didn't get rid of this one. Well, we can just start here. We'll start at the last one. Okay, my last one is the square root of x plus 3. Is my graph here linear or nonlinear? Nonlinear, right? It curves right here. It's a nonlinear function. Let's take a look at the next one. So let's do, it's x minus y equals 12. Linear or nonlinear? Well, this one is pretty clearly linear, right? Straight line. So that one we're going to write linear. Let's take a look at our next one. Y equals 3 minus 2x squared. Linear or nonlinear? Obviously nonlinear, right? We have a downward facing parabola. Nonlinear. My next one, I have y equals 5x. Linear or nonlinear? Straight line. This is linear. Last one, if I put in, what is this one? Y equals 2 to the x. Linear or nonlinear? Obviously nonlinear, right? There's a big old curve right there. Not a straight line. Well, we can find a pattern. Let's see, here we go. We can find a pattern. I'm just going to write, just in case you no, yes, no, yes, no. Okay, we can find a pattern in what our functions look like in terms of their equation that will clue us in on how we can figure out whether or not a function is a linear function just by looking at the equation. So if you look at this and notice, what do the ones that are not linear have in common? So this one is not linear. Let me do it in a different color maybe. Let's try green. This one is nonlinear. This one was not linear. And this one was not linear. Right? What do each of these equations have in common? Well, each of them has an exponent that is not 1. Right here, I have an exponent of x, definitely not 1. Here, I have an x squared. And this one's a little trickier, so the square root of x can be written as x to the 1/2. So this is kind of like saying x to the 1/2 plus 3 also does not have an exponent of 1. So a very quick and easy way to decide if a graph is going to be linear or nonlinear is if it's linear, my x will have an exponent of 1. And I'm using x, but I mean my independent variable, right? So whatever might be in the place of x. I might not always use x, but my x is going to have an exponent of 1. It will be linear. A nonlinear function, then, if it's not linear, x has an exponent of something that's not 1, right? So, whoops. Okay, x has exponent that doesn't, come on. Exponent not equal to 1. A linear function, my independent variable, my x value is going to have an exponent of 1. A nonlinear function, it will not have an exponent of 1. Okay, good. Now we have an example. So the linear function y equals 1.25x represents the cost y in dollars of x bottles of orange juice. Each customer can buy a maximum of 5 bottles. I need to find the domain of the function, decide if it's continuous or discrete. So I'm going to start there. I think it's easier to think about, is it continuous or discrete first? So a discrete domain is going to have individual points, right? They're not going to be connected. A continuous domain is going to have values that are connected to each other, so that I have a full range. I can have absolutely any number in that range. Well, if I think about this in terms of our problem, right, we're looking at bottles of orange juice. I can't go to the grocery store and buy a fraction of a bottle of orange juice. I can only buy a whole bottle of orange juice. So my domain is going to have to be whole numbers. So I know that it's going to be discrete because it's not continuous, because I can't have a fraction. So I could buy 0 bottles, right? I could buy 1, 2, 3, 4. It's a maximum of 5, which means that I can include 5, so I could also have 5 bottles. So my domain is discrete. My values are 0, 1, 2, 3, 4, and 5. Okay, we're going to start with this graph down here. You're going to have to extend it 1 because I forgot to add another column there. I'm going to write our equation up here so I don't forget. Y equals 1.25x. Okay, so if I have 0, 1, 2, 3, 4, 5. Obviously, if I buy 0 bottles of orange juice, it's not going to cost me anything. If I buy 1 bottle of orange juice, I've got $1.25. 2 bottles of orange juice will be $2.50. 3 bottles of orange juice, $3.75. 4 bottles of orange juice will give me $5. 5 bottles of orange juice will be $6.25. Right? All I'm doing is I'm taking my x value and I'm plugging it in, so I'm multiplying all of those by 1.25. Okay, so now I need to graph it. One of the most important parts of graphing a function is I need to label my axes. So this is my x-axis, right? This is my y-axis. My x-axis has my bottles. So down here I'm going to have however many bottles. Then over here, it's going to be my cost. Ooh, it doesn't like me writing upside down, so we won't do that. I'm going to have my cost. Okay, so I'm going to have a point at 0, 0. Oop, that is not at 0, 0. This might not work very well. We'll try though. Okay, 0, 0. 1, 1.25. So 1, 1.25 is here-ish. 2, 2.5. 1, 2.5. 3, 3.75. 1, 2, 3.75 up here somewhere. 4, 5. 2, 3, 4. 1, 2, 3, 4, 5. obviously this is not super precise because we're using fractions, but I'm trying my best to be as close as possible. And then 5 and 6.25. So 5, 1, 2, 5, 6.25, somewhere in here. Okay, this is my entire graph. I have plotted all the points that I can plot. I am not going to connect these points because it's not a continuous graph. This is a discontinuous graph. Okay, our next example, a runner's speed is 5 miles per hour. The number of miles run, m, is a function of the number of hours, h, spent running. How does this situation represent a linear function? Well, linear functions, we remember, have constant rates, right? It's always going at a constant rate. This is telling me that my runner is running 5 miles per hour. That's a constant rate, right? So yes, this is a linear function because it's a constant rate. Okay, my domain of my function. So in my first case, my domain was discrete, right? Because I could only buy whole bottles of orange juice. The domain of this one, right, is how many miles I have gone. And I can run any number of miles, right? Like I could run 1.25 miles. I could run 3.6 miles, right? I can run any of those things. So this is going to be a continuous domain. And my domain is just going to be x is greater than, I'm going to put or equal to 0. Because I could not go any miles, right? And then I would just go 0 miles at 0.5 miles per hour. So anything greater than or equal to 0 is going to be in my domain. Obviously, there's probably a cap to it. You're not going to run 100 miles at a time, but for our purposes, right, it's just going to be that x is greater than or equal to 0. So now we want to graph this. So what is changing all the time is my time here determines how many miles that I have gone, right? So time, miles. I'm going 5 miles per hour. So let's say right here I've got 0.5. Let's put 1 here. 1.5. I don't think I'm going to be able to have space for all of this. When I have gone a half an hour, if I have been running for a half an hour, how many miles have I gone? Well, I'm going to take 5 divided by 2, right? Half an hour. So that's going to be 2.5. So I'm going to put a point here. Okay. After 1 hour, I have gone 5 miles, right? 1, 2, 3, 4, 5. Ooh, that was not at all what we wanted. Let's try this again. Oh, come on. Okay. 5. After an hour and a half, I've run 7.5 miles. 1, 2, 3, 4, 5, 6, 7.5. Okay. I'm not going to fit 10 because it's not on this space. But if I had been running 2 hours, it would be 10 miles. Now, I decided that this is a continuous graph, right? So really, this is not very good. Okay, well, we're going to connect these dots the best that we can because this is a continuous graph. That's not, it should go through 0, so it's not great, but you get the idea. Right? Okay. Come on. Okay, complete each table for the sequence of similar rectangles. Graph the data from the tables and decide whether the pattern is linear or nonlinear. So I have this rectangle. My width is x, my length is 2x. So what I need to do is I need to figure out my perimeter. So when x is 1, I would have 1 plus 1 plus 2 plus 2. So 1, 2, 3, 4, 5, 6. When x is 2, I would have 2 times 2, so I would have 4. 2 times 2 is 4 plus 8 would be 12. Right? I would have 2 here, 2 here, 4 here, 4 there. So I have 4 plus 8. Ooh, not what I wanted. Eraser. Okay, and then let's see. For 3, I would have 3 plus 3 is 6. 2 times 3 is 6, so I'd have 12 plus 6 is 18. Okay, and I can look and see, well, I'm going up 6 every time. So if it's at 4, this is a constant rate. This is going to be at 24. This is going to be at 30. Okay, so then I would graph it. Is this going to be a linear function or non-linear? Kind of gave it away, right? It's increasing at a constant rate. So this is going to be linear. Now let's look at area. Area is length times width, right? So when x is 1, my area is going to be 1 here. 1 times 2 is 2. 1 times 2 is 2. So I'm going to, if my area is 1, or my x is 1, my area is 2. If x is 2, I have, come on, I want the eraser. If x is 2, right, I have 2 here, whoop, 2, this is not working great, 2. And then 2 times 2 is 4, so then 2 times 4 is 8. So when my x is 2, my area is 8. Clean that up a little bit. All right, if x is 3, right, this becomes 3. 3 times 2 is 6. 6 times 3 is 18. I can already tell, am I increasing at a constant rate? I'm not, right? So I already know that this is going to be non-linear because I'm not increasing at a constant rate. I'm just going to have you go ahead and fill out the rest of, so find what 4 and 5 are, and then graph these over here. So, right, so for example, I'm going to have 1, 6. So 1, 1, 2, 3. This is not going to go very well for you. You might want to change your scale a little bit. So let's do like, I don't know, let's do 2, 4, 6, 8, 10, 12, 14, 16, 18. I'll at least get my first 3 dots on there. So I would do 1, 6 is my first dot. Oops. And so on and so forth, right? So graph that one. Do the same thing with the second one. So this is going to make a straight line, right? It's linear. It's going to make a line. Oh, goodness sakes. It's clearly time to be done. This is going to make a line. My second one, the area is non-linear, so it's obviously not going to make a line. It should be a curve of some sort. So go ahead and finish this table and do your graphs.